2 in the morning, an empty intersection. One car waiting at a red light, and 12 seconds later, the light changes. No timer did that. The intersection saw the car, not with a camera, with something buried in the road itself, hiding in plain sight at a huge share of the world's signalized intersections. Those dark lines cut into the asphalt? That's the machine. This is the wire that watches. And once you see it, you can never unsee it. So many of the intersections you've ever crossed have been hiding the same secret. Rewind to the 1950s. Most intersections still ran on fixed timers. Green for one street, then green for the other, around the clock, whether anyone was waiting or not, which meant empty streets got the green, while a queue sat idling at the red. Drivers stuck at 2 a.m., held for a cross street no one was using. Engineers needed the signal to know one thing: is anyone actually there? And it wasn't a new problem. Some early signals had tried to feel you coming. A few changed only when you honked your horn at them. Others buried pressure plates in the road, metal contacts that closed under a car's weight. Those could sense a car on their own, but they cracked under traffic and wore out fast. The answer that finally stuck arrived in the early 1960s, the inductive-loop detector. No moving parts, nothing for a tire to crush, just a coil of wire and a shift in a magnetic field. And it has run the world's intersections ever since. For decades, retiming a signal meant manual traffic counts, a person, a corner, and a clipboard. To be fair, fixed timing never fully died. Downtown grids still run on coordinated timers by design, but out in the suburbs, where demand comes in unpredictable lumps, detection wins. Here's what's actually in the road. Crews saw a shallow slot into the asphalt, a rectangle roughly 2 meters on a side. Into that slot goes ordinary insulated wire, looped around the rectangle, typically 3 turns, then sealed under a black, rubbery filler. That's the dark outline you see. A lead-in cable runs from the loop to a cabinet on the corner, the gray box you've walked past 1,000 times. Inside that cabinet, an electronics unit drives the loop with an alternating current, tens of thousands of cycles every second. And that turns a rectangle of wire into something remarkable, an electromagnet, projecting an invisible field up through the asphalt. The wire itself is nothing special, the same gauge you might find in a lamp cord. The magic isn't the material, it's the geometry. On new roads, crews sometimes skip the saw entirely. Preformed loops are laid down before the final asphalt goes over them, born inside the road. Now, the physics. The loop and its electronics form a resonant circuit. It oscillates at a frequency set by the loop's inductance. Drive a car into the field, and the field doesn't just pass through it. It induces whirlpools of current in the car's metal underside. Eddy currents. By Lenz's law, those eddies create their own field, opposing the loops, and the loop's inductance drops. When inductance drops, the oscillation speeds up. The frequency rises instantly. That's the entire trick. Electrically speaking, a car is a disturbance in the field, and the loop feels it. If you want the formula, it's the one engraved into every first-year engineer. Frequency equals 1/2 pi, root LC. The capacitance is fixed. The inductance is the lever, and the car is the hand that pulls it. How sensitive is that, really? A typical loop oscillates tens of thousands of times a second. The spec change, 0.02% of inductance, moves that pitch by only a few hertz. The detector hears a 5 hertz change in a 50,000 hertz song. And here's the misconception worth killing. This is not a magnet attracting iron. An all-aluminum car triggers a loop just fine. What matters is conductivity. Anything metal enough to host eddy currents will sing. And as long as the metal stays put, the frequency stays shifted. The loop doesn't just see you arrive, it knows you're still there. The detector in the cabinet watches that frequency like a hawk. The standard specification says it must catch a change of just 0.02%, 2 parts in 10,000. Car arrive, the frequency jumps. The controller gets the message, lane 1, vehicle present. Your green light is now in the queue. The first loop detectors were analog. In 1975 came digital units, far more reliable, with tunable sensitivity. Software programmable detectors followed in the 90s. Today, a single intersection can run a dozen loops, counting cars, measuring queues, and timing every phase of the cycle around real demand. Loops also run in two modes. Pulse mode fires once as you cross, perfect for counting. Presence mode holds the call for as long as you sit there. That's what keeps your red light request alive. On freeway ramps, the same loops feed ramp meters, the lights that drip cars onto the highway one at a time to keep the flow from collapsing. But there's a catch, and every motorcyclist already knows it. Here's the twist. On paper, a motorcycle should trip the loop easily. Centered on the wire, it moves the inductance several times more than the detector needs to fire. So why do riders still get stranded? Because two things rarely hold. The sensitivity turned all the way up, and the rider parked dead center. To keep from answering the next lane, engineers turn it down, and a motorcycle stopped shy of the wire barely couples at all. A bicycle has it worse still, right at the threshold or below. Which is how a rider ends up trapped at a red light that never, ever changes, invisible to the machine. The fix riders swear by is real physics. Stop directly over the wire where the coupling is strongest. Sometimes that's all it takes. Engineers can also turn the sensitivity up, but push it too far, and the loop starts seeing trucks in the next lane. Detection is a balancing act. Some cities paint a small bicycle symbol on the asphalt. That's not decoration. It marks the exact sweet spot over the wire, where a bike has the best chance of being seen. And loops do have an Achilles heel, the road itself. When pavement cracks, shifts, or a utility crew saws through the wrong spot, the loop goes dark. That's the price of living inside the asphalt. Modern controllers even watch the watchers. A loop that goes silent for too long, or starts chattering nonsense, flags itself for maintenance. In some places, the law itself acknowledges the problem, letting a rider treat a dead red light as a stop sign after coming to a complete stop. If that sounds like your way out, check your local rules first. A rider's trick at the stop line is a workaround, not a fix. So engineers went after the real target, reshaping the loop itself to reliably catch even a bicycle, the one vehicle that truly does sit near the detection floor. Simply cranking the sensitivity up brings back that same problem. The loop starts answering for cars in the next lane over. Engineers call it splashover. So rather than turn up the volume, they reshape the antenna itself. Cut one more slot down the middle, and the loop can be rewired into a figure 8. It's two halves now, carrying current in opposite directions. Far from the road, those opposing fields cancel, so the next lane falls quiet. But right at the surface, directly over the wire, the field stays sharp and strong. This is the quadrupole loop. The figure 8 is just how it's often drawn. It is what finally lets even a bicycle sit at a light and be seen, and the Detector Handbook recommends this very pattern at the stop line. The turns of wire are a dial of their own. More turns, more inductance, and more sensitivity, wound to suit the lane. Even the cable back to the cabinet is engineered. Run as two straight wires, it would act as an antenna for hum and radio noise. So it is twisted tightly together, and the noise, induced equally in both, cancels itself out. And once you know the trick, you start seeing loops everywhere. On freeways, where loops were first used to count traffic, they now measure speed and flow, feeding the signs that warn you about congestion ahead. Put two loops a known distance apart, and timestamps become speed. Distance over time, a radar gun's math, without the radar. At parking garages and gated entries, a loop is what lifts the barrier as you roll up to it. Rail systems have used them as wheel detectors. Drive-thrus use them to announce your car. Toll plazas, car washes, automatic gates, the same quiet rectangle everywhere. Same wire, same field, same little jump in frequency. Remember, the loop's one real weakness. It lives inside the road. That's exactly what sent engineers hunting for something to replace it. Installing one means sawing open a lane and putting a crew out in live traffic. And exposed to every freeze and every resurfacing, some loops last only a handful of years. So challengers arrived that mostly avoid cutting the asphalt. Cameras on poles, watching detection zones drawn in software. Microwave radar, ranging vehicles from the roadside. Even small wireless sensors that feel the dent a passing car makes in the Earth's own magnetic field. Each one sidesteps the saw cut in the lane, but each brings its own trouble. A camera can be blinded by fog, glare, or snow. Radar and wireless units cost more and carry quirks of their own. And still, the humble loop holds its ground. Properly tuned, it is among the most accurate presence detectors we have, and it does not care if it is midnight, pouring rain, or buried under snow. Cheap wire, settled physics, nothing above the road to blind it. The technology everyone keeps trying to replace just will not leave the road. Back at our empty intersection, the car rolls onto the loop. The field shifts, the frequency jumps, and the controller hears it. 12 seconds later, green. Not magic, not a camera. A rectangle of wire and physics discovered nearly 2 centuries ago, working the night shift. Beneath every smart city is a lot of very patient wire. Subscribe to Beneath the Wires, and we'll keep showing you what's under there.